Hello, ladies and gentlemen, my physical science students. Mr. Escock's back. We are talking about the periodic table, and now we're going to hit into the families today. But first, let's talk about some of the trends that we talked about last time. When it comes to trends, you can say that the density goes up as you go down the periodic table. You can say that the density decreases. So as you go down the periodic table here, density goes up. Goes up. As we go from right, density decreases. You can say that as you go down, the size increases. As you go left, right, the size decreases. An element's position on the periodic table can tell you a lot about it. The most reactive groups, like right here, are your alkali metals. They are in group 1. They are right here. Right here are your alkali metals. Group 17 over here are your halogens. They are very, very reactive. Alkali metals only have one valence electron. Halogens need only one. So losing one, gaining one makes them very, very reactive. Group 18 is the least reactive. Most of the atoms of the periodic table are metals. When on your periodic table, your alkali. All of the alkali metals form a positive 1 charge. These are your halogens here. They all form a negative charge. Noble gases are here. Metals tend to stay on one side. All of this is where your metals are found. Over here are your nonmetals. Now, what makes something a metal? Metals are shiny. They conduct electricity. When we call it shiny, we call that luster. Because they conduct electricity, we draw them into wires. We call that. And they're malleable, meaning that they can be pounded in thin sheets. Gold can be pounded very thin, like aluminum foil for that matter. The first group, the alkali metals, is by far the most reactive. It has a lone electron in its valence shell. And that lone electron is easily lost. When you lose an electron, you become positive. So let me show you one. If I take lithium, 3 protons, 4 neutrons, it'll have nucleus, so it'll have 2 electrons in this first. You know, it has only one in this outer shell. It gives that up freely. This is the valence shell. The second group are the alkaline earth metals. They have two valence shells, or valence electrons, and they lose both of them. Well, when you lose two valence electrons, positive two. The transition metals are located in the middle of our periodic table. They're used in all kinds of industry: copper, silver, gold, iron. Mercury is used in a lot of things for electronics now. Cadmium, platinum, some other real famous ones. Iron, used in all kinds of things. Copper wire, copper pipes, copper in your electronics. Tungsten in the old-fashioned light bulbs even. So the alkali, the alkaline earth, down in here you have the transition. They're called transition because they shift their valence electrons between 1, 2, and 3. Speaking of transition metals, a man stole my gold yesterday and I ran after him yelling, "Hey you, give it back." Sorry guys, bad sign. The rare earth metals are towards the bottom of the page. They are actually clipped to make the periodic table a little bit easier to work with. These are the rare earth on here. And they actually belong right in here. They're used in a lot of fancy electronics and modern technologies now. Nonmetals and metalloids have a wide range of characteristics, and they start at the zigzag line and move over. A nonmetal is the exact opposite. So metals conduct heat, nonmetals don't. Metals conduct electricity, nonmetals don't. Metals are shiny, nonmetals are dull. Metals are easily pounded. If you pound on a nonmetal, it'll break. Some common ones, sodium's a metal, excuse me. Nitrogen and oxygen, they're both gases in the atmosphere. Bromine is actually a liquid at room temperature. Carbon is the most important atom for building life molecules. Now we get to the other special groups, the halogens. The halogens are the most reactive nonmetal. Fluorine is like the bully of the periodic table. Fluorine has such a high electron affinity, meaning a desire to grab other electrons, that it can pull electrons from almost anything. Fluorine, chlorine, bromine, iodine, and astatine are all there. They get their name as a part of the halogens because when they react, they form salts, which we used to call halides. So those of you who are playing along at home, these ones have a +1 charge, +2. Everything in here is +1, +2, or plus, depending on what you are using. The bromine or the boron group all +3 because they lose 3 electrons. Now carbon has 4, actually plus or minus 4. Nitrogen has 5 valence electrons and it wants to gain 3, it'll become a -3 charge. Oxygen gains, so it becomes a -2 charge. Here's our halogens. All halogens become a -1 because they only want one more valence electron. And then your noble over here. They do not want to gain any charges. Noble gases are group 18. They're referred to as inert or non-reactive. The most common in the Earth's atmosphere argon, we use it in windows, and then we use neon lights all the time in different fancy signs. Now, the metalloids are around the zigzag line in the middle of the periodic table. They are commonly used as semiconductors, especially in your electronics. You have silicon chips for all kinds of things. My metalloids, I get a different color here, are in this green. If the most important metal right there, that one is silicon. Those metalloids follow the zigzaggy line here. Very, very important because they don't conduct perfect electricity and it slows things down to make different types of circuits. Sometimes you can change your identity. We call this radioactivity. Radioactivity basically is kicking parts out of the nucleus because it's too big. So generally you kick out 2 protons and 2 neutrons out of the nucleus. Well, when you kick out two protons, you have actually changed 2 spots to the left on the periodic table. It actually produces a lot of energy that way, and we can detect radiation using a special device called a Geiger counter that actually picks up the pings of the particles. Some radiation can cause cancer, but we also use radiation to kill cancer in some cases. I've had friends who had radiation done to kill certain tumors and things. It usually burns their skin, though. It doesn't look like it's a fun thing to go through. They use radiation for different types of monitoring systems, like different types of radiation. And obviously, large doses of radiation is a problem. When it comes to radioactive decay, we can find out that it is remarkably steady and very, very accurate. Once scientists determine the age it takes for something to go from 1/2 of its substance, we call that a half-life. So basically, you start with an isotope of, say, uranium, and after so many millions of years, that uranium is divided in half. That's the half-life. If it takes 300 years for a 10-gram sample of an isotope to decay to 5 grams, that's a half-life of 300 years. In another 300 years, that 5 grams would actually decay into 2.5. So in 600 years, it would be less. Every time you use this, it's usually for aging a rock or some sort of like dinosaur fossil that will tell you the age or how long ago that lived on Earth. Let's do a little quick review here. So with the periodic table, as you go down, density goes up, atomic size goes up. As you go across, density goes down and atomic size goes down. If you form a positive ions tend to be larger. Your negative ions tend to be larger. There's not as much control. Actually, the protons can't pull those electrons in. All right, ladies and gentlemen, I hope you have gathered a lot from this. I'm Mr. Hescox. I'm about out of time on the amount of time I can use in this video. If you need me, see me, email me, send me a remind. Until next time, be good, be safe.